Greetings. So this course is about online algorithms. Probably you're not familiar yet with this notion. So an algorithm, I hope everyone knows what an algorithm is, but an algorithm or a problem is called online if it doesn't have access for all the input in the beginning of its run, but it gets its input as a sequence. So, for example, just an input in a stream or by actually being a web page, so it's online, the sequence, and the input is usually denoted by the Greek letter sigma, and the parts of the input are just indexed by numbers. So this means that the input is a vector of several requests. So we get the first part of the input, and after some time we get the second part of the input, and then after some other time we get the third part of the input, and so on. But for each request we have to respond immediately, and it has to respond to each sigma I by some action. The output is usually called action in this subject, and usually the actions are denoted by tau I. It's also a Greek letter, by some action tau I. And to determine your action, you only knowing only. So we don't have access to the future, so we know only the past. So the past sigma 1 till sigma I or I minus 1, but not the future. So we have to decide without knowing what will happen next. Well, it's life, but not the future. Sigma I plus 1, blah blah m. And we do not even know the length, the total length of the input. So we do not know m. Okay, so a request comes, we immediately have to serve the request by some action, and then another request comes, we have to serve that guy immediately, and so on. And to each action sequence, say tau, usually I'm underlining vectors and not underlining not vectors, so tau, there is a cost associated. So there is an associated cost which you want to minimize. Cost. This cost of tau is usually denoted by the C of tau, C for cost of tau to be minimized. Now, of course, it's very general, so I will start with an example problem, a toy problem if you wish, which is called the ski rental problem. Also for an input sigma, there is an optimal solutions cost, which is usually just denoted opt. So for input sigma, the cost, the optimal, the minimum possible optimal cost of a possible action sequence is simply denoted by opt of sigma. Now, in many cases, the cost of an action sequence also depends on the input, so sometimes I will use a sigma subscript here as well, but it's I'm usually dropping those indexes which are not fully used. So I'm just moving to an example to make it more understandable. So the type problem, which you will see several times during this semester, is called the ski rental problem. The ski rental problem. You can look this up on the Wikipedia webpage, of course. The ski rental problem. The underlying scenario is that we are on holidays on a mountain or whatever, but there is either snow on each day or there is no snow on that day, and completely independently from the surrounding days. So the input for a ski rental problem is just a sequence of bits. So sigma 1, sigma 2, and so on, sigma m, and each sigma I is either 0 or 1. Either 0 or 1. So basically 0 means there is not enough snow to go skiing, and 0 means there is no snow or not enough snow, whatever. And 1 means we can go ski. Well, not only can, but we go for skiing that day. But initially we don't have skis, and we either buy or rent skis. So an action, possible actions are, first type of action is to buy, and this means that we buy a pair of skis, and we of course keep it. Skis for a cost of b. Greater than 1, of course. It's usually an integer cost, and it's determined in the beginning, so it's fixed. The price of the skis doesn't change with time. Fixed in the beginning. There is also another option to rent. Rent means that we pay one amount of money, so unit cost, but we only rent the skis for 1 day. A pair of skis for that day for a cost of 1, for a unit cost if you wish. So of course it's cheaper to rent than to buy, but if you buy, then you won't have to rent and you won't have to buy anymore, because you will own the ski you bought. In this case, you are able to skip. Skip, we don't spend money, so it's a cost of 0. But it's allowed only if either there is no snow so if there is no snow, so if the current input is 0, or if we already bought a pair of skis. And of course we want to minimize the total cost we pay, but we don't even know in advance the length of the season. So for example, if the price of the skis is say 4 and the input sequence is say 0, 1, 1, 0, 0, 1, 0, 1, 1, say, and then some possible action sequences are, for example, I can just keep renting and never buy the ski, which means that I'll skip, I will rent on the second day, I will rent on the third day, because it's also a snowy day, see, so it's here I'm just renting for this day, here I'm just renting for this day, but then there is no snow in the next 2 days, so I'm just skipping, but after that I'm just renting and renting and renting. So that's a possibility, just to keep renting. In this case the total cost is 5, because there are 5 days, 1, 2, 3, 4, 5 days, so its cost is 5 because we pay a unit cost for each snowy day. Or another possible output sequence is, say, I can just buy the pair of skis on the very first snowy day if I wish. So on the first day there's no snow, so I'm just skipping. But on the next day there is snow, so I'll buy the ski. But from that point on I don't have to rent, I don't have to buy, which is encoded by just skip, 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 skip and skip. Now in this case the cost is 4, because the parameter of the input b was 4, so the price for which I bought the pair of skis in the very first snowy day is 4, but I don't have to pay anymore. Or I can decide, say, just buy the ski on the third snowy day, say. So I'm just skipping, I'm renting on the first 2 snowy days, but on the third snowy day I'm just buying the ski, and from that point on I'm allowed to skip. Now that's even worse than the first one for this particular input, because I'll have to pay twice renting cost and once buying cost, which is 1 plus 1 plus 4, it will be 6. So amongst these three inputs, this guy here is the best, and actually this is optimal. So if you just think a bit, then you can deduce it that this guy here for this input is optimal solution. So in general, well, usually n denotes the number of snowy days, so the number of ones in the input. So it's just the number of ones in the input. And we have that the optimal cost is easy to compute if you have access to the future. So if you know in advance all the input sequence, the whole input sequence, then you just have to compute the minimum of the cost of the skis and the number of snowy days, because if it's in a situation like this when there are more snowy days, then it's a best bet to buy the ski on the very first day, and then you are just ending up with a cost of B. Or another option is just keep renting and renting and renting and renting and renting, which is a good choice if there are not too many snowy days. So for example, if this point is the end of the input, then this first one, just keep renting for a cost of 2, is a better choice than buying the ski because it costs more. So in general, if there are not too many, say less than B days with snow, then N is better. But as soon as you will have at least B days, and you have at least B snowy days, then it's a better choice, and it's an optimal choice to buy a pair of skis on the very first snowy day. So the offline optimum is this one. But since you do not know this part in advance, you won't be able, in all situations, I will put the correct one, because you don't have access to the future. We do not know N in advance. However, we know B, so the price of the skis is announced, so that's what we know always. And there are many possible algorithms, so I will just say that so some possible algorithms which are online, I guess you already have some of these in your mind right now. So some possible online algorithms for these problems are, say, for example, the first one is just to keep renting. That's fine, so you can do this without knowing the future. Another one was, which we already tried, not on our input, is just buy on the first snowy day, no matter the cost. The first snowy day. And of course there is another one, say buy on the third. If there are 3 snowy days, which you don't know in advance, but so you on the first snowy day you will just rent, and the second you will just rent, but on the third one the third snowy day. So it's just third snowy day. Third, yeah. And so on. I guess you can just come up with some possible algorithms. So all of these guys are deterministic. They don't involve any random number or random choice. And for a week, so for this week, we will just analyze these type of algorithms called deterministic algorithms. A deterministic algorithm means it's not random. If you get the same input sequence, then you will outproduce the same action sequence as well. Now, these algorithms are usually denoted by large A for this problem, and with an index of so with the index of the day on which we decide to buy. So in general, AT will buy on the 10th snowy day. On the 10th snowy day. So A3 buys on the third, A1 buys on the 4th, and as an extension, A infinite is used to denote this keep renting algorithm. Now we have a couple of algorithms, and the question is, which is better? How should we measure the performance of these algorithms? That's the question, and that's the main question of the subject. So we can't really say that one of the algorithms is always better than the others. So for example, if again I'm just trying to use this v=4 setting again. So if I will get this sigma like 0, 1, 1, 0 and 0, and that's all, then, well, in this case the A1, A3 and A infinite will just output these guys. So I'm just skipping and buying and skipping and skipping and skipping. A3 will just skip and rent for 2 days, and since there is no third snowy day, then it's fine. And this keep renting algorithm will keep renting no matter the cost. So basically here we spent 4. So the cost of these algorithms are respectively 4, 2 and 2 at this point. So at this point A1 is the worst and the other 2 are better. But then if I'm just keep adding ones, then A1 will just again skip because we already bought the ski. A3 will just buy the pair of skis at this point because there were already 2 of the snowy days and it's the third one, so A3 says that I buy the ski on the 3rd day. And the infinite will just keep renting. Now in this case the cost of the algorithms are 4, this guy became 6 and this guy is 3 respectively. So here the A3 is worse than both of the other guys. So in the previous step A1 was definitely the worst, and now for this input A3 is worse than both of the other 2. And also if I'm just keep adding say 4 snowy days, then A1 will still have a cost of 4 because it just skips and skips. A3 will have skip because both a pair of skis at that point, so it will have a cost of 6, and this guy here, a infinite, will just keep renting and renting and renting and renting. So here we will have a cost of 7, and in this case a1 is the definitive winner and a infinite is the loser for this particular input. So there are cases when one of the algorithms is better, but the same algorithm will become the worst in some on some other input, on some other particular input. And that's why we usually measure the algorithms by their so-called competitive ratio, which is just a ratio of the output produced by the algorithm and the optimum cost. So the measure is an algorithm A is, say, X competitive, here X is a number, so for some we will see that X is at least 1 if for each possible input sequence sigma we have. So as I've said, if I run the algorithm A on this input and check the cost of the solution of the action sequence produced by the algorithm, and I just divide it by the optimal cost for this particular sigma, that's always upper bounded by X. So that's the relation that has to hold. So basically, so for example, in 2 competitive, for example, 2 competitive means that it spends at most twice the necessary cost. At most twice. The optimal solution. And say the 1.1 competitive means that it will just spend 10% more than the optimal solution. So we will say that an algorithm is better if it has a smaller competitive ratio than some other algorithm. So, for example, again, we can just list some of these inputs. So 1, 1, 1. Okay, so these AT algorithms are not really affected by the zeros, by the presence of the zeros, because they just keep skipping for free for those inputs, so I'm not including zeros at this point. So for these things, I'll just try to measure the A1, the algorithm A2, and the algorithm A3, and the algorithm A4, and the algorithm A infinite, and I will also try to list the optimal cost for the setting of B equals 4. So here, okay, and then I will just use once, but say 100 times. So if there is 100 snowy days, there are some snowy days. So for example, A1, if it gets this particular input, then immediately it will spend its money and buy the skis. and it basically behaves the very same way in all the other scenario, all the other listed scenario, because on the occurrence of the very first one, it will buy the keys for a cost of 4, and it will just skip the remaining part of the season. At the same time, the optimal cost for these things are, say, 1, because it's better just to rent if the cost of the ski is 4. Now the optimal cost for the second case is just 2, the optimal cost for the third case is just 3, the optimal case for the fourth, it doesn't really matter if you just keep renting for 4 days or buy the pair of skis for on the very first day, the cost will be 4. In the fifth scenario, it's definitely better to buy the skis. And then in the 100 snowy days scenario, it's also better to buy the skis for a cost of 4. Now the ratio, and I could do this all day, so I could just check all the possible inputs, but okay, so here I'm just moving back there. What should I do? So this is the ratio which we will always try to compute. It's just the cost of the algorithm divided by the optimal solution's cost, and I'm just curious what's the maximum or the supremum if a maximum doesn't exist. So what's the maximum possible value for the algorithm divided by the optimum cost? And that will be the competitive ratio of the algorithm. So for example, here at this point, A1 spends 4 times more money than it's necessary. Here it's only 2 times more, here it's only 4/3 times, and for all the other cases it spends the optimal cost. But the worst possible scenario is this one, when the A1 spends 4 amount of money, but the optimal should cost only 1, so it's the ratio between these two quantities is 4. Yeah. Now, just to analyze all the other algorithms quickly, A2 just rents on the very first day, so the cost in this case is only 1. That's fine. But if we have 2 days at least, then it will pay a renting cost for 1 day, and then it will pay 4 units of money more to buy the skis. So for example, here the cost will be 5, because on the very first day it will rent, and on the second day it will buy. So it's just the RB sequence, which has a cost of 5, and then there is RB, skip, RB, skip, skip, RB, skip, 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 and so on. So it always spans 5, and so on. Now here, the worst possible ratio is on this row. 5 divided by 2 is 2.5. So it's 5 divided by 2. I prefer fractions. So that's the maximum ratio. So it's 1/1, it's just 1. 5/3, 5/4, and these guys are smaller than 5/2. And similarly, so this already shows that for b equals 4, A2 is considered to be a better algorithm than A1 because it has a smaller competitive ratio. In each possible scenario, it will just spend at most 2.5 more money than it's strictly necessary, while A1 can end up by spending 4 times more money. So it's how it's measured. Now for A3, we will have this column because it's just 1 renting, it's just 2 renting, and in the third row we will get 2 renting and 1 buying cost, which is 6. So it's just rent, and then buy for 4, because again we will have this 4 as parameter, right? But from this point on we will have 6 and 6 and 6. Now the worst possible ratio for this particular algorithm is 6/3, which is 2. So it says that A3 is even better than A2 because it will spend at most twice as much as possible or strictly necessary. And again 1, 2, 3 and 7, 7, 7 and so on. Now in this case we have 7/4, which is even smaller. Now you can have the impression that it always decreases, but okay, so I just include the A5. So A5 is just spending money like this, 8, 8 and so on. Right, so it will just keep renting on the first 4 days, and then it will just buy the ski on the 5th day, but for a renting cost of 4 and additionally a buying cost of 4. Now in this case we have the worst possible cost here, 8/4, which is again 2. So it's worse, it just became worse than A4. So it seems that among these algorithms A4 is the definitive winner, but if you just compute the costs of the keep rent algorithm and 5, at this point it seems to be very good, but if you have 100 winter nights then you will end up by 100/4, which is already 25, but you can just add zeros, so you will have 1,000 winter days. In that case you will end up by a ratio of 250, and actually you won't have an upper bound for that. So in this case there is no maximum, but it's not a competitive algorithm, because if you just increase n and n goes to infinite, say, then the ratio will also tend to infinite. So it seems that amongst these algorithms this A4 is the best possible, because the competitive ratio of this algorithm is the smallest amongst these guys. And actually we can just prove it. We will do that. So there is say proposition the competitive ratio in general ratio of AB, it wasn't a coincidence that A4 was the seemingly best possible algorithm for the case when B equals 4. So AB is the algorithm which buys on the bth day, where B is the price of the ski. So it's should be an integer, of course. Of AB is exactly 2 minus 1/B. Now, proof. How do we prove such things? Usually, when we want to prove a competitive ratio of an algorithm, we do a case analysis. A case analysis for all the possible inputs. For all the possible inputs. So it's very general. So usually we don't make such tables and just write down all the possible input sequences, because there is an infinitely many of them. So usually we make clusters or cases. In this problem we only have 2 cases. The first case is if the number of snowy days is smaller than b. Then the optimum cost, remember the optimal cost is always the minimum of n and b, which is if n is smaller than b, so it's just n. And the algorithm's cost, which is usually denoted by H. Okay, so we are running a B. A B just keeps renting and it buys a ski on the bth snowy day. But there are no b snowy days, which means that it's just renting for n days as well. So in this case, the algorithm divided by the optimal cost is just n over n, which is 1. Now that's fine. We've already seen such things, because if I'm just going back here, so here for example 2 over 2 was 1, that's fine. 3 over 3 is 1, that's fine. If the ratio is 1, that means that the algorithm computes some optimal solution for this particular input. And this is exactly when n, the number of days, is still smaller than the price of the skis. But as soon as we will have b snowy days, situation will change. So the second case is that if b is smaller than or equal to n, then the optimum is b, because it's the minimum of n and b always. And the cost of the algorithm is the following. So AB buys the pair of skis on the bth snowy day, and so on the first b minus 1 snowy days it will just keep renting and renting and renting. Plus on the bth snowy day it will just buy the skis for the cost of b, and basically that's all, because after buying the ski it will just skip, 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 skip and skip. So it's 2b minus 1. And the ratio is, in this case, the algorithm's cost divided by the optimal cost is just 2b minus 1 divided by b, which is, so I have here 2b over b is 2, and I also have here minus 1 over b. And this is of course larger than 1. So since I have to compute the competitive ratio of an algorithm, I will just have to take the maximum of these two values, and since b is at least 1, 2 minus 1 over b is also at least 1. So if we increase b, then this value will become larger. And so the maximum is exactly 2 minus 1 over b. Exactly this is the same what happened here. So here we had 7 over 4, which is exactly 2 minus 1 over 4. Yeah. So we have proved that the competitive ratio of this algorithm is actually 2 minus 1 over b. And in the next video we will see why is this an important proposition, because as a spoiler I will tell you that this is the best possible competitive ratio for a deterministic algorithm for this problem, so you cannot do really better. But that will be the part of the next video. Till then, bye bye.